welcome to Wolverhampton University. It's a great pleasure today, as part of this Institute of Physics evening lecture, to welcome Dr. Thomas Taylor. Tom Taylor, I've never understood why you chose your name like that, but Tom, who is a reactor physicist at Moltex Energy. I've seen on your CV that it was also called Moltex Energy Canada. You will tell us about the structure of the company, maybe.
Yeah.
And a quick introduction about our speaker. I've just mentioned he's now a senior reactor physicist working for that. He graduated from Warwick, then went to Southampton where he did the PhD. There we met for the first time. We even wrote a paper together.
Yeah.
Connectivity.
Everyone?
In the group of Alexei Karuki. Good coming. And Tom, after graduating his PhD, then started to work for the energy industry. First, I believe with EDF.
Yep.
I should say EDF.
EDF, yeah.
EDF, but that's the French company, Electricité de France. And I'm French myself, as you see from my accent. So, well, he worked for this for a while, and then he moved to the reactor physics business, and you raised in importance, I believe, because now you are quite high in the company, and you actually designed this molten salt reactor, of which I hope to hear about, because it's some very interesting phase of matter. So it's a great honor to welcome you, dear Tom. One last anecdote, if I may, because I mentioned we met some time ago with your friend at this time. One day, Tom kindly invited me to have the British Sunday roast at his home. And there was a beautiful picture of the baby on the wall. And then I learned that he was doing modeling as a baby, because he was such a pretty baby that selected as representative of what is most pretty.
Wow, I'm amazed you remember that.
That's the only thing I would remember when I forget everything else. So dear Tom, the floor is yours.
Thank you.
You have a tradition at this IOP lecture after the talk, which is the most interesting bit, but we like very much the audience to engage with the speaker. So don't be shy, ask questions about everything, about the science, about everything that comes to mind. Dear Tom, please.
Okay. Alright, I better go over here because the microphone's there. So, good evening, good afternoon, everyone. And thanks very much to Fabrice for inviting me to talk. So as Fabrice said, I work for a business called Moltex, and I'll tell you a bit more about them later. But I'm going to start a bit more generally, trying to set the scene a bit, I suppose. So I'll give a bit of a general introduction, and then I'll ask the question as to what role nuclear should or could play in our energy system. We've seen that there's been a fair bit in the press recently about the energy mix and how we best generate our electricity, produce low carbon energy. So that kind of sets the background. And I'll talk about the nuclear power that we have operating at the moment in the world, how we generate our electricity in Europe and the UK, and then I'll go on to talk about some advanced reactors, so the kind of next generation of reactor, and the molten salt reactor that the Moltex are designing is one of these advanced reactors. So don't want to scare you. That's the reactor physics of advanced reactors rather than advanced level reactor physics. I'm not expecting we're going to have time to get into that. So and then I'll finish by focusing on a couple of advanced reactor designs in particular, and then tell you a bit more about the Moltex designs. Okay. So given we've recently had the anniversary of Russia's invasion of Ukraine, it seemed a good place to start. We've all felt the impact of that war on our electricity and our gas bills, and the impact that's had on fossil fuel prices and the cost of living in general. So there's a recent article here that suggests that the war in Ukraine has directly cost the equivalent of about £1,000 per adult for every adult in the UK. So this has clearly had a big impact. There's some Office for National Statistics data here for electricity and gas prices, which shows how severe that is. So this kind of throws into focus the need for our energy to be affordable, first of all, and we often maybe take that for granted in previous years when electricity has been relatively cheap, but these kind of events really highlight how dependent we are on fossil fuels for our energy, and in being dependent on those fossil fuels, how we are susceptible to shocks from events outside of our control. Now, we also know clearly that we need to take action to mitigate the impacts of climate change and reduce the impacts of climate change. So we are already probably starting to see the impacts of climate change, and this plot on the left shows some data from the Met Office, which shows the increase in sort of extreme events which we would expect to be more likely as a result of increasing surface temperatures. So we need energy which is affordable and which is also secure and reliable, but we really need to address the climate emergency and stop ourselves following the really scary scenarios on the right, the higher lines on the plot, which give us many degrees of warming. So how are we going to change our energy system in order to address climate change, in order to get towards net zero? So a bit of data, first of all, starting with an example from Germany, which has been incredibly successful really in increasing its share of renewable generation. So it's a real success story to be applauded that they have managed to increase the solar and the wind generation significantly. That's, as I say, that's a real success, and we clearly need more renewables as much as far as we can to get to net zero and to decarbonise our electricity supplies. Now, nuclear. Germany has a well-known nuclear phase-out policy, so I guess that's part of the reason for looking at Germany as an example. In the growth of renewables, they have chosen the path of phasing out nuclear and trying to reach net zero with a focus on renewables alone, or at least renewables forming the bulk of their electricity generation. And that has the kind of recent crisis associated, or gas price increases associated with the war in Ukraine, have prompted some debate in Germany about the role of nuclear. So there's been a short delay in their phase-out policy in order that they could get through the winter and not be quite so susceptible to the gas price increases we've seen. So a bit more data now, which I think is interesting. Now I should say first of all, I'm not claiming that this data is fully representative, but I think it's some data which shows how carbon intensive the production of electricity has been over a kind of subset of the Western world. This data covers 25 days. So as I say, it may not be representative, but it still shows, I think, some interesting trends if we look at the extremes. So if we start at the top, the lowest carbon intensities are from countries which are blessed with hydro or geothermal energy resources. So Scandinavian countries, Quebec, Iceland with its geothermal energy. The next one on the list is Ontario, which I'll come back to. But if we then go down the list a bit further, we see Great Britain, and the grey line shows our target for 2030. At the bottom is Poland, and I suspect we are familiar with why Poland is at the bottom. They generate electricity predominantly by burning lignite or brown coal. So that gives a high carbon intensity in terms of grams per CO2 equivalent for a unit of electricity generation. Germany is not very much higher up relative to Poland, and that reflects the fact that they also burn significant amounts of brown coal to supplement their renewable generation. I mentioned Ontario. Now, I can't claim to be unbiased, clearly, but I think this is a nice illustration of the benefit of nuclear generation. Ontario generates the vast majority of its power from nuclear. It's the most populous province in Canada, and they use their indigenous can-do design. France is a little bit further down the list, but not too much further. Again, we know that France produces its electricity predominantly from nuclear. So this is an aspect of energy production, consumption, that is clearly going to be very important if we are going to achieve net zero. We need to reduce the carbon intensity of our electricity, and we need to decarbonize other forms of energy, so transport, manufacturing. So I didn't bring this up, but this picture here just shows a map of Europe. You won't be able to see that hugely well, but the yellow signifies that gas generation is the largest source of electricity. That's all right. So I'll just explain this part further while I come in. So yellow is for gas, that being the majority source of electricity generation. Green is nuclear, blue is hydro, geothermal, black is coal. And then we've also got the light blue being wind power. Hi everyone. Great to see so many faces. You haven't missed too much for those of you that just come in. I've just been trying to set the scene a bit. My name's Tom Taylor, by the way. I'm from a company called Moltex, and I'll tell you a bit more about Moltex later. But I've just been setting the scene in terms of what's often referred to as the energy trilemma. So the need to generate, or the need for an energy system which is affordable, is secure, and is sustainable. So those are the sort of three main areas that we need to satisfy if we have an energy system which is fit for purpose, and most importantly, in my view, allows us to reach net zero. So, yeah, I was just saying this plot on the right compares the main source of electricity generation for various countries across Europe, from the UK, which is mainly gas, to countries such as France, which are nuclear. Okay, so I'll move on. So the next question, I suppose, is given the need to satisfy this energy trilemma, to produce energy in a way that's affordable and secure and sustainable, what role should nuclear play in that? And again, I don't claim to be unbiased, but I will try and present pros and the cons of nuclear. So the first thing that we should address is safety. That's clearly a concern around nuclear, and I would argue, others would argue, that nuclear power, modern designs in particular, are extremely safe. And there's some data here which attempts to compare nuclear to other forms of energy generation in a way that quantifies the impact of other sources via air pollution or greenhouse gas emissions, for example. Nonetheless, nuclear is different to other forms of energy generation. It is obviously, fuel is radioactive, we all know that, and an important consequence of that is shown in this little picture at the bottom here. So, this is a pellet from a thermoelectric generator, so a device that converts heat to electricity, and that's done typically using a radioisotope that decays as it does so, producing heat, which can be turned to electricity. So this shows this pellet is glowing red hot, basically due to the decay of plutonium-238. So this makes nuclear different. Why is that? That's because if we shut down a nuclear fission reaction, we don't shut down immediately the generation of heat, and that was what ultimately caused the Fukushima accident, was the inability to remove the heat which continues to be generated even after the fission reaction has stopped. So that makes, as I say, nuclear different to other forms of generation, and modern designs achieve very high levels of safety despite the need to deal with decay heat by adding layers of engineering safety to the designs effectively. And what we see is that comes with a cost. So this plot shows the cost of nuclear power in dollars per kilowatt as a function of time. So we can see that since the 70s, the early days of kind of commercial power generation from nuclear, to the present day, with the example here of Hinkley Point C, nuclear has got more expensive, and one of the main drivers for that has been the increase in safety levels, which has been achieved by adding layers of engineering complexity to increase safety. So this is clearly an issue with nuclear. We need our energy to be affordable. We've already said that, and some would argue that nuclear is not affordable, and that can be argued depending on how you account for the costs of what the alternative would be. I suppose the costs of burning fossil fuels instead, as an example. Okay. Now the other big thing we need to address in a conversation about nuclear is waste. That's obviously a big concern, and for very, very understandable reasons. Nuclear power produces spent fuel waste, which is very radioactive for hundreds of thousands of years. So just unimaginable timescales, really. And the solution to the problem of what to do with that waste, or the internationally accepted solution, is deep geological disposal. So this picture at the top shows, I think, Sweden's design. The Scandinavians, as with many things, are kind of leading in terms of getting their house in order to actually be able to store spent fuel waste in these repositories. So here you're talking 500 metres or so underground, building tunnels, containing that waste in a form which which can be shown with high confidence to be stable for the kind of timescales we're talking about here. So that's quite a big problem, and that cannot really be denied. That's a problem which the industry believes it has solved, but it's a big barrier to public acceptance of large-scale nuclear power. Just to explain this part on the left, the red curve on the right shows how the radiotoxicity, which is a function of the radioactivity, but also how that affects the human body, how that decays as a function of time. We've got a reference on here, which is sort of natural uranium ore. So, as I said, that takes hundreds of thousands of years to significantly reduce. Now, there are things in principle that can be done to reduce the timescales. So, there's a couple of things that are indicated here. The first is to remove uranium and plutonium from the spent fuel waste, and if we do that, we reduce the time for which that waste is a problem by about an order of magnitude. And then the other thing we can do is to remove not just the uranium and the plutonium, but all the minor actinides. So the other things that are in spent fuel, the americiums, the curiums, those sort of things. And if we do that, then what we're left with is the fission products. So the lighter elements you get when a heavium is split in fission. Those mostly have much, much shorter half-lives. So if you can do that, and we'll come back to this later, then you change the timescales dramatically, and in principle it becomes a more solvable problem with technology that is hopefully more straightforward than the deep geological repository. Okay, so I've spent quite a long time trying to set the scene and trying to present some of the issues, the pros and cons around nuclear power. You can question me at the end if you don't think I've done that. So let's move on to talk a bit more about nuclear power now. So we'll get on to advanced reactors, but first of all, just to explain the history and the current technology that we use. So we tend to talk about generations of nuclear reactors. The first generation being the post-war designs, which were initially sort of research reactors, and eventually the first commercial reactors like the Magnox at Calder Hall. The picture at the top right is the Wilbur Magnox, which operated until 2015 very successfully. So that was probably the last of the first generation of nuclear reactor. The second generation are the reactors which are generally operating today. So the advanced gas-cooled reactors, which operate in the UK, the light water reactors, which are the dominant technology used around the world. Canada is the Canadian design, RVMK is the Russian design. And then if we move into sort of the last 20 years, the designs that have been developed since maybe the 90s, then we're talking about the third generation, or sometimes 3+, to distinguish some of the more modern designs. So the EPR, which is being built at Hinkley Point C, is of that generation. That is a light water reactor, a pressurized water reactor, and it's distinguished from generation 2 by basically the level of safety that's achieved by the increased engineering complexity of the station that I referred to earlier. So the bottom left shows the construction site at Hinkley Point C. Bottom right is an AGR at Hunterston on the west coast of Scotland. I spent a bit of time there when I first started working for EDF. It's a stunning spot just opposite the Isle of Arran. So yeah, you can see there's a magnet station there, which is decommissioning, and then an advanced gas-cooled reactor. Okay, so how about advanced reactors? When I'm talking about advanced reactors, I'm going to assume that's the same thing as a generation 4 reactor, basically. So we've talked about generations 1, 2, and 3 of nuclear. The next generation, generation 4, are advanced reactor designs, which are fundamentally different in design to any of the reactors any of the commercial power reactors which operate today. So there is an organisation called the Generation 4 Initiative Forum. I may have got that wrong. Anyway, the website's here, gen4.org. They did some work to narrow down the kind of generation or the advanced reactor designs which exist, and to kind of form a body which helps cooperate design of advanced reactors. So they narrowed down to 6 designs. I've missed one off here, but I'll come back to that. So there's some schematics here, and if you're interested, I recommend going to this website. They have a very, very accessible report which looks at the different designs, the pros and cons. So we've got, just to quickly explain the acronyms, a very high temperature reactor, molten salt reactor, sodium fast reactor, the gas cooled fast reactor, and the lead cooled fast reactor. I'll talk a bit more about these as we go through. Now, these designs are next generation in that they are aiming to be a kind of step change in the performance of these reactors, and performance in terms of these 4 areas: so safety, sustainability, efficiency, and cost. I'm going to focus particularly on a couple of these, on the sodium cooled fast reactor and the molten salt reactor. So we'll talk a little bit more about those. But first of all, just to explain a bit more about the kind of philosophy behind these designs. As I said, the safety, the level of safety that's been achieved with the current, most recent reactor designs that are being built or close to operation has been achieved through layers of engineering. So there is a hazard that is present, and in order to prevent that hazard actually causing people or the environment any harm, you add a lot of redundancy, diversity. You effectively engineer the design such that if something goes wrong, then you have another barrier that prevents that something going wrong actually leading to release of radioactivity. And as we said, the implication of that is increases in cost and complexity. Now, the best way to address safety, to make something more safe, is to just remove the hazard completely. If, obviously, we can design a nuclear reactor that has no radioactive fuel, then great, problem solved, but it wouldn't be much good. But we can remove hazards that might be slightly less fundamental. I'll talk about some of those in a minute. So the advanced, or the Generation 4 reactors, are aiming to make reactors more safe by eliminating hazards, or by substituting a hazard for something which is less serious or lower risk. And in principle, what that does is it makes the reactor much simpler because you don't need all the layers of engineering, and you therefore get increased safety at lower cost. That's the idea behind these designs. Okay. Right, so I was going to move on to some physics. This is what I want to talk about, really. So I'm going to kind of touch on a few areas of the physics of advanced reactors. So first of all, I should maybe start with just a quick introduction to what reactor physics is. So we know that in a nuclear reactor, we're producing heat by fissioning heavy elements like uranium or plutonium. So when a neutron hits one of these atoms, it has a chance to undergo fission, creates 2 lighter elements and some heat, which we are going to make use of to generate electricity. So the job of a reactor physicist, broadly, is to be able to understand, in the core of a nuclear reactor, how the neutrons are moving around, being transported around that reactor core, and and also therefore the reactions which those neutrons are undergoing. So fission being one of those reactions. In order to generate heat, we need a certain number of fission reactions to give us a watt of heat, let's say. And the amount of reactions we get are broadly determined by two things. One, how many neutrons do we have in a certain amount of space? And the other thing is, how likely is it that some plutonium or uranium we've got in the fuel is going to capture one of those neutrons, fission, release some heat, and some other neutrons which are going to continue the controlled chain reaction that we want in our reactor. So the advanced generation 4 reactors are kind of split into two camps. Thermal or fast reactors. And most of the reactors that operate today, almost all of them, are thermal reactors. And what that means is that although neutrons are, when they emerge from a fission event, they're moving very, very quickly, they have very high energy. At those high energies, the likelihood of an individual neutron causing a fission in an individual nucleus is relatively low. So if I come to this plot on the left, we've got cross-section on the y-axis, which effectively expresses the likelihood of a given reaction. And we've got neutron energy on the bottom, which you can think of as neutron speed. So when a fission occurs, neutrons are released, and they're released up at this end in the kind of mega electron volt range. But the cross-sections, the likelihood of fission reactions up at those energies is relatively low. So what most reactors do is try and moderate those neutrons down to thermal or lower energies, where the cross-sections, the likelihood of fission becomes much, much greater. So in a water reactor, we've got water there which is moderating neutrons, and effectively all those neutrons are doing is hitting hydrogen atoms and losing some of their energy. So thermal reactors, the neutrons which are causing fission are down this end. In a fast reactor, the neutrons are staying up here where they're born, effectively, where the energies they're released from fission. And in between is this kind of horrible looking region where generally we don't want to be. And the reason that we don't want to be in that region is that all these sharp peaks are resonances where quantum mechanical effect means the reaction is more likely. So in that energy region in the middle, it's much more likely that a neutron is captured by a uranium-238, say, and does not undergo fission than it is captured by something and causes fission. So we want to keep our neutrons up at the energies they're born. That's what a fast reactor is trying to do. Therefore, we don't want any moderators. We don't want to lose neutrons into this region where they're much less likely to cause fission. Or we want to get them right up to the other end where fission is much more likely. Okay. So just to explain briefly the plot on the right, I've said that in a nuclear reactor we rely on a chain reaction, controlled but nonetheless a chain reaction. So one fission releases some heat, but it also releases another couple of neutrons which can go on and cause other fissions. Now, for most of the energy range, the number of neutrons you get on average from a fission event is pretty flat. Maybe 2.5 or so for uranium-235, or a bit higher for plutonium-239. Up at high energies, there's suddenly quite a dramatic increase in the number of neutrons that you get from a fission event. And that means effectively that you have more neutrons available to continue your chain reaction or to do other things, as we'll come on to next. So that's an advantage in principle with using fast neutrons as opposed to thermal neutrons. So when we're when people talk about fast reactors, the kind of history of fast reactor development was from relatively early days in the development of commercial nuclear power, when the known uranium resources were relatively low, and particularly compared to, at that time, the extremely optimistic ideas as to the success of nuclear power. In the early days, there are quotes such as "too cheap to meter." The idea that nuclear power would be incredibly successful and be the dominant source of electricity generation. So there were concerns, effectively, that there would not be enough uranium available to be mined to turn into fuel to operate the nuclear power that the world wanted. So a way to address that issue is by using a fast reactor to breed its own fuel. So when you hear talk about fast reactors, they often come along with this idea of breeding. And all that means is if we put some fissionable material or fissile material into our reactor, then we're going to be generating heat by causing fission, but these excess neutrons we have, we need two neutrons for a chain reaction, one to cause a fission, one to go on and cause another fission. As long as we have that steady state at 2, then we can have a sort of self-sustained reaction. Any extra neutrons, they can do things like leak out the reactor or be absorbed in other things like the metallic materials we've got in the reactor, but they can also go on and cause reactions which actually produce more fissile material, and that's breeding. So there's something called the conversion ratio, which expresses the ability of the degree of breeding, and that's just if I've got what's the ratio between the new fissile material I'm producing and the fissile material I'm destroying by fissioning it. So the two typical ways this is done. The first one is based on uranium-238, captures a neutron, becomes uranium-239. A couple of beta decays later, it's then plutonium-239, which is a nicely fissile isotope. So if we have some neutrons to spare, and we can allow those to be lost at one point in time, but in doing so, they then generating fuel that we can burn later in a subsequent reaction. You'll also hear people talking about thorium. So the other way of breeding is based on thorium. That's much less typical, but is another way that you can breed fuel. So we use this idea of conversion ratio to express the degree to which new fuel is bred. If that ratio is greater than 1, then we're producing new fissile material more quickly than we're destroying it. If it's less than 1, then we're gradually depleting the amount of fissile material in our fuel. And we refer to that as burning to distinguish it from breeding, because the net effect is to burn the actinides that are present in your fuel. Okay. Right. A little bit more physics before I move on. Again, this is a cross-section. So again, this is expressing the likelihood of a certain reaction. And here we're looking at 2 reactions in one isotope. So the isotope is plutonium-240. And the reactions we're looking at are capture. So neutron is captured, nothing else happens apart from an emission of some gamma. And that's in green. And red is fission. So we said we can operate reactors either up at fast energies, where neutrons are born, or right down at the lower thermal range. And for isotopes or nuclei like this, there's a dramatic difference in what's likely to happen to a neutron. And we can see that because at the lower end, at the thermal end, we have many orders of magnitude more likely that a neutron is going to be captured by plutonium-240 than it is to cause a fission. If we have neutrons up at these high energies, then the opposite is true. And this is important for a couple of reasons. So One of them is related to waste, because if we can make fission possible in all the actinides we have in our fuel, then we will destroy by fission all of those higher actinides, which we saw contribute a lot to the radiotoxicity of spent nuclear fuel. The other thing is that it increases the performance of the reactor by making more of the fuel able to undergo fission effectively. Okay, so a break from some physics, I suppose, just to look at a couple of the designs in a bit more detail. So the most common advanced reactor design, this has been operated in many places, although not at a commercial scale, is the liquid metal fast reactor. So that is a nuclear reactor which is where the fuel is being cooled by liquid metal. It's kind of a strange idea, but it's using a liquid metal which is typically sodium or maybe lead as the coolant. It's a fast reactor, so it's using high energy neutrons to fission. And this picture shows the kind of iconic Dounreay fast reactor, which is an early prototype reactor that was built in the north of Scotland. So there were two fast reactors built at this site, the Dounreay fast reactor and confusingly then the prototype fast reactor, which operated until sometime in the early 90s, I believe. And a number of other countries have operated these kind of liquid metal fast reactors. So these four pictures all show sodium fast reactors that have operated or are operating. In the case of the left-hand reactor, that's a Russian design which is operating now, called the BN800. EBR2 was a reactor in the US. The top right shows the largest of these type of reactor that's been built, which was a kind of commercial scale reactor called CPhys in France, and this is Monju in Japan. So this is by far the most well-developed design if we're talking about generation 4 reactors, and there's a lot of experience in operating these. There's in terms of physics at least, there is one kind of difficulty associated with the design of this type of reactor. So another set of cross sections. Sorry, I might be sick of these by the end, but what we're looking at here is cross sections for sodium. So I said that most of these liquid metal fast reactors are using liquid sodium to cool the fuel. And I also said that these are fast reactors, therefore we want the neutrons to stay at the high energies at which they're born. Now what these cross-sections show is the likelihood of, first of all, scattering, elastic scattering in blue, and secondly, neutron capture in red. So both of these are kind of undesirable reactions. The scattering because in colliding with a sodium nucleus, the neutron loses energy, and that's bad for where we want our neutrons to be. Capture is just removing a neutron from our chain reaction. So these two reactions are kind of an unavoidable byproduct of the fact that we need something to cool our fuel with. And sodium's pretty good as a coolant. As a liquid metal, it's got really high thermal conductivity. It's dense, it's got a high heat capacity, so it's great as a coolant. However, if we look at this red line on the right-hand plot, is a kind of schematic of the distribution in energy of the neutrons in this reactor. So most of our neutrons are up in the sort of mega electron volt range, close to where they're born. However, this is a logarithmic scale, so there's big changes here, but there is a relatively significant tail of neutrons which are being moderated to lower energies by this sodium. And there's a big resonance that you can see leads to a big depression in the neutron flux. What that means is at that energy, it's very unlikely you'll find neutrons because the reaction in sodium to scatter them somewhere else is very likely. So with sodium fast reactors, this causes a particular issue in design, a particular physics issue, and that is that if sodium is cooling your fuel, then we've said that we want our neutrons to stay up here. But the more sodium we have in our reactor, the more our neutrons are scattered down to the lower energies, where they're going to be less effective in continuing the chain reaction. So let's imagine now that for some reason, let's say a fuel channel gets blocked, or there's something which causes the fuel locally to heat up, and that starts to locally cause some kind of boiling of the sodium. Then what that does is, so we're effectively reducing the density of sodium in that location. And if we do that, then we're making these reactions less likely. So we're making it more likely that neutrons are going to stay up at the high energy range where we want them to be and where they were more favourably fissioned. So this basically is a positive feedback. If something happens to increase power or temperature that causes the sodium to reduce in density, then that increases the power further. And this is not something that any nuclear reactor wants. We need negative feedback so that as power or temperature increase, the reactions get less likely and bring the reactor back to a stable position. Now this doesn't mean you can't design a safe sodium fast reactor, but it adds complexity to doing that. And I picked it out because I think the physics of it are interesting. Whether I've explained them properly is another matter. Okay, so let's move on from the sodium fast reactor. The other advanced reactor I'm going to focus on is the molten salt reactor, and there's an obvious reason for that, which is that that's what we at Moltex are designing. But first of all, these are two very early molten salt reactor designs, both experimental reactors in the US. So the one on the left is particularly interesting because that was actually called the aircraft reactor experiment. It was a nuclear reactor that was designed to power aircraft, which seems a terrible idea, but at the time that was what they were considering. That led to another design which was for a more typical power reactor. This one's called the molten salt reactor experiment. So what you can see here is the core of what is eventually the reactor. It's graphite, basically, which is going to contain the fuel. It's going to moderate the fuel and channel the coolant over that fuel to remove the heat. Now, these type of reactors in principle have a number of advantages. They have some disadvantages too, which I'll come back to. But starting with safety, a big advantage of a molten salt reactor is in the feedback behaviour. So I just talked about the stability we get if we have negative feedbacks. Now, a molten salt reactor has a very, very strong negative feedback. And the reason is that molten salts, their density changes quickly with temperature. So if we increase the temperature of a molten salt, it becomes less dense, and that reduces in this case, because we've got, I should explain first of all the fundamental of a molten salt reactor, which is that it is a liquid salt which contains both the fuel and the coolant. So the schematic which we saw earlier is basically molten salt flowing into a region where it can become critical, where the fuel in it can sustain a chain reaction. It does that for a period while it's in this region. It then flows out of the region where it's possible for that reaction to be sustained because of geometry or the materials present. And it then passes through a heat exchanger to give up its heat before passing back through. So one of the design attractions of those kind of reactors is they're incredibly simple. You just have a single liquid salt which is circulating between a region where it produces heat, or can be critical and produce heat via fission, and a heat exchanger where it gives that heat up to produce steam. So if that salt has the fuel in it, which is actually needed to sustain the reaction, then if it gets hotter, becomes less dense, then the main effect of that is you have less fissile material in a given space, and therefore the reaction is strongly damped with increases in temperature. So that is referred to as inherent safety. Basically, the physics of the reaction means that the power cannot increase continuously. The chances of a fission chain reaction being sustained just drop dramatically as the temperature increases. The fuel is already liquid, so there's no possibility of melting fuel, which is what happened at Fukushima and caused the accident. There is no need for any pressure. These salts are liquid up to very high temperatures, so you don't need to, in contrast to a water reactor, you don't need to pressurize it in order to keep that material liquid. And that has a lot of advantages for design and for safety, because there's no force to drive the material elsewhere. And the salt chemically contains a lot of the radioactive material you get from fission. So even if an accident were to occur, then there's no radioactive material which can be released and become airborne or dispersed to release radioactivity to the environment. Okay, I won't go into the other ones. I'm a bit conscious that I'm probably taking too long. So there are disadvantages as well. So a big advantage is simplicity, but this molten salt chemically is very complex. It's corrosive. It's flowing around the circuit at very, very high temperatures, and it's very radioactive. So the operational difficulties associated with that are quite significant. Okay, I'm going to skip those slides. I'll just talk quickly about some of the designers that are working on advanced reactors in the UK. So there's Moltex Flex, who is the company that I work for, designing molten salt reactors. UK Atomics are another company working on a molten salt reactor. Westinghouse, who are a large nuclear company, are designing a lead-cooled fast reactor. U-Battery is a high-temperature gas reactor, which I've not talked about too much, as is X-Energy. And then abroad, there are many more companies trying to develop Generation 4 or advanced reactor designs. Okay, so I'll finish with a little bit about Moltex, the company that I work for. So Moltex is actually two businesses. Moltex Flex, which is the UK-based company that you've seen the logo for on the slides, and Moltex Energy Canada, which is developing a different molten salt reactor design in Canada. So the Canadian side of the business is developing a fast reactor, a molten salt fast reactor, and we have a customer for that reactor, which is New Brunswick Power. So it's the utility that operates New Brunswick's nuclear power station. So that reactor design is in the process of review by the Canadian regulator. In the UK, there's a different design being developed, which is thermal, so low energy neutrons using low enriched uranium. And we've got a lab in Birchwood near Warrington that's doing a lot of work for both designs. Now, Moltex, we're developing molten salt reactors, but they're different to the molten salt reactor I described a couple of minutes ago, which is this simple idea of a single salt which you're pumping around a circuit into a region where it can be critical, out of that region to give up its heat and circulate it back round. The Moltex designs sacrifice some of the simplicity of a standard molten salt reactor in exchange for removing some of the issues around corrosion and having a circulating radioactive salt. And the way that's done is basically by now having two salts instead of one, a fuel salt, which is contained within pins in a core, and a coolant salt, which is circulating as in a standard reactor to cool that fuel, transfer the heat to the secondary circuit. So this is a little bit more information on the Canadian design, which I'll let you read, but I'll pick out one of the most important things I've not touched on is it uses recycled nuclear waste as fuel. So I said I would come back to waste earlier. This reactor, because it's a fast reactor, I said one of the advantages of a fast reactor is it can fission any of the heavy elements, basically. So we can put spent nuclear fuel, which has lots of plutonium, but also americium and a bit of curium, things like that, into our reactor. We can fission that to generate energy, electricity, but also to reduce the problem of what to do with that spent fuel waste. So this is just a schematic of that. This is being developed in Canada, as I said, so it's based on using spent fuel waste from the CANDU reactors, which are operating in Canada. So we said the spent fuel, the accepted solution is to dispose of it in a geological repository. We would like to instead recycle that fuel in a way that we can use it as fuel. We can generate more electricity from that, and we can then massively reduce the waste that comes out the other side that then needs to be disposed of. The UK design is simpler. It's based on uranium for markets where there is no spent fuel available, where you want to generate electricity using a standard uranium-based fuel. So this reactor design is all about simplicity, and the name Flex comes from the idea that these reactors can be used to support a grid which is heavy in renewables. And the way that's done with both of these reactors is using energy storage. So we talked earlier about the need to decarbonise electricity. We also talked about the fact that a lot of our energy is not electricity. It's transport or it's manufacturing. So for decarbonisation of those areas of the energy system, high temperatures are a big advantage. We can, if we have high temperatures, then we can maybe produce hydrogen or synthetic fuels, or we can use that heat directly for processes, for manufacturing processes. The other thing we can do is use a molten salt to store energy that our reactor has produced. And there are these big solar power plants that you may have seen pictures of in the desert. They use this technology already to store the electricity, the energy or the heat that's generated by the reactor. And what this means is that you can have a reactor operating in a steady way, but you can store the energy and use it when it's needed, when the wind's not blowing, for example. And it can operate in a similar way to the gas power stations, which we really rely on to balance our grid. Okay, I think I'm out of time, so I'll stop there. If you feel free to ask me questions about the difficulties of the physics, but yeah, otherwise, just to finish, these designs are they're not commercially demonstrated, so there are challenges associated with getting these technologies to a point where they can make a difference to reaching net zero. But yeah, our view is that they can make a very important contribution, and we need to develop these designs quickly in order that they can have a significant impact in actually allowing us to reach net zero, but still in a way that's affordable and secure. I'll stop there, I think. Thank you.
Thank you, Dr. Dr. Taylor for all these cross-sections and details on the nuclear reactor. So as I said at the beginning, the main point of this procedure is to do the public, to speak to the speaker. So don't be shy, please ask. So, any doubt that you
Yeah, please do.
Yes, we got a question over there.
So you mentioned earlier that Moltex is developing a sort of a different approach towards the reactor, as in you're splitting the salt in two parts. So how are you going to make sure that that coolant salt will not experience the same thing as the sodium, as in neutron capture, or it will not be corrosive?
Great question. So you're exactly right that in principle, when you separate the fuel from the coolant, then that makes you susceptible to the same issue that I talked about for a sodium reactor, which if your coolant is reducing the energy of the neutrons, then if you make that less dense, then that increases the chance of fission reactions. The reason that's much less of an issue for a molten salt reactor is the thermal expansion effect I talked about. So if, for example, the temperature of our fuel increases, which would then reduce increase the temperature of the coolant and lead to that effect, the dominant effect is actually from the fact that the fuel has got less dense. So physically the fuel gets hotter, it expands, that immediately makes acts as a very strong negative feedback. That completely overwhelms any impact from the coolant. In a sodium reactor, you don't have that effect because the fuel is solid. It doesn't expand significantly as temperature changes. So you have some feedback from the fuel, which is negative and is very important in a sodium reactor, but it's not nearly as significant as with a molten salt. Could you repeat the second part of your question? I know.
Is it just that you're going to design the salt so that it's not corrosive? A lot of the molten salts are not inherent. They're not necessarily corrosive. If the chemistry is well controlled, then there's no reason a molten salt should be corrosive. The issue comes if you do not understand the chemistry of the salt, or you lose control of the chemistry of that salt. And if you have a salt which contains your fuel, then when a fission happens, you split a heavy atom into two light atoms, and you create a range of nuclides, many different isotopes. Those decay. So you create the chemistry of that salt becomes incredibly complex, and that is what makes the corrosion issue more difficult. You also then have the fact that if you do have some corrosion, your whole circuit is very radioactive, so maintenance of that circuit becomes much more difficult.
More questions?
Yeah.
These are lovely renderings, I guess the one on the left is New Brunswick.
That's right,
and the
yeah.
one on the right's somewhere in the UK.
Yep.
How representative do you think they'll be of the final site?
I
think that's how they will look.
I mean, I guess not, in honesty, but fundamentally, just to pick out some details on the drawings, the reactors here for the flex are these pod-like buildings. The reason we've got lots of these is they're quite low power. They're deliberately very low power because that makes it easier for them to be extremely simple. So that's the reactors. Over here we've got molten salt storage for energy storage, and you can see something similar over on the left-hand side in that picture. So the Canadian design has one extra thing, and that is the facility that's actually recycling the spent fuel to produce the fuel for our reactor. So that's the reactor is kind of more in the foreground at the front here, and the grass-covered building behind is the facility which will recycle the spent fuel waste. So these pictures are representative in terms of what the design looks like now. I guess the details will change as we go through and develop the design further.
Thank you. More questions?
Yep.
Is there a standard for like the quality of the radioactive waste in order for it to be recycled? or will it do with any waste in storage?
It won't.
Used?
So it does have an impact, and quality is a good word actually, because although I said that with fast neutrons, any of the heavy elements in principle will fission, any of the actinides, there are still some that are more likely to than others. So plutonium-239 is the most has a very high probability of undergoing fission. So depending on the spent fuel waste, there will be varying ratios between different plutonium isotopes and other isotopes. So that affects the reactor physics of that fuel when it's in the reactor. Now, a fast reactor in principle is very, very flexible. It should be able to operate with a range of fuel compositions, but there will be limits. What we've done is to model the spent fuel that's available in Canada. Also looked at the waste that's available in somewhere like the US. Those spent fuel waste can both produce fuel for our reactor. They'll behave slightly differently, but there's no reason that we can't use all that waste. Yep.
It's more a question about fast reactors generally rather than thermal ones.
Mm.
If you're relying on fast neutrons, how do you prevent the reactor from going prompt critical?
Good question. So, I guess just for those that don't know, prompt critical is due to the fact that when neutrons are released from fission, you get the majority are released almost straight away. Those are prompt, released at prompt timescales. You get some which are referred to as delayed neutrons, which are released seconds, even minutes later. Those delayed neutrons are extremely important for the way a reactor operates, basically because prompt neutrons initiate a chain reaction which proceeds very, very quickly. So your reaction can change on timescales which are very difficult to control. So a reactor relies on the prompt component dying away, and the little boost you get from the delayed neutrons is what actually keeps the chain reaction going. So in a fast reactor, you still have prompt and delayed neutrons. And exactly the same applies. You are still relying on those delayed neutrons to keep your reactor in a stable position, and you never want to reach a position where the reaction can be sustained on prompt neutrons alone. The difference is just that you're trying to keep all those neutrons up at a high energy range rather than thermal, I suppose. Did I answer your question there?
I think so.
Yeah.
More questions? One here.
For the molten salt reactor, like say there's an emergency, how would you stop all the fission in the field?
Yeah. Okay. Yeah. So the way that's done in a reactor that's operating today, for example, is typically with control rods. You probably know this. So that's inserting a neutron absorber into the core effectively to mop up some neutrons and stop the chain reaction. So in a molten salt reactor, you can, in principle, have exactly the same method. You also have some. You also have advantages from the inherent safety. So this is something that people will talk about a lot for advanced reactors. What if, in a standard reactor, what if the control rods don't insert for some reason, and you therefore can't shut your reactor down, and you've had some kind of fault which is increasing power? That's clearly a very, very serious situation. And the power can increase quite substantially and release quite a lot of energy before the natural feedbacks terminate that. In a molten salt reactor, the feedbacks are so much stronger that if a fault were to occur which was increasing power, then the natural feedbacks of the reactor will shut it down. And that will happen much more quickly than in a typical water reactor. You still probably don't want to rely on that alone. You want to be in full control of your reactor at all times, so there will be systems which will stop the chain reaction in the event of a fault before
that inherent safety is relied upon, but it gives you an extra level of safety beyond the engineering or design.
I was interested about timescales.
Yeah.
Tonight.
Yeah. Okay. So I'll start with the Canadian design. The Canadian design is a bit more complex because we've got two technologies. We've got the spent fuel recycling to produce the fuel for the reactor. So that facility needs to be operational before the reactor. It needs to be operational for a period of time to produce the fuel for the reactor. So we're looking at the early 2030s timescale to get that operation, to get that kind of facility operational. The UK design has slightly more ambitious timescales because it's a very simple design and it uses standard uranium, or it uses uranium as fuel, so that is available on the market. So the aim there is to have the first of kind operating before the end of this decade, before 2030, and then to build subsequent units in the early 2030s. So that relies on a number of things. The kind of next milestone for us is entering some kind of regulatory process, whether that be the UK GBA process or something similar.
We've got a question over there.
Quick question, when it comes to salt's corrosive nature and the fact that many of the salt's reactors using lithium, we're going to generate tritium, which is very small, and then the conclusion is unescapable that actually we're going to release that to the environment.
Yeah.
How Moltex is planning to stop that?
So the Moltex philosophy that was kind of indicated on an earlier slide is, if there's a hazard, then the first question is, can we remove that hazard? So the answer is basically not to use lithium. So the salts that both designs use do not contain any lithium. They don't contain beryllium either, which is another common salt constituent because it's extremely toxic. So they are fluoride or chloride salts which don't contain lithium.
So we don't generate any tritium in that?
No, there are some reactions which will still generate tritium, but they're much, much less likely, so the amounts are tiny.
Thank you.
In terms of safety and fuel supply, still using thorium pellets as a fuel be better?
So thorium is, if you look at a lot of the early publicity around Moltex, it typically refers to three generations of design. A uranium-fueled reactor, thermal reactor, fast reactor was using spent fuel, recycled spent fuel, and then a thorium generation later. So there is no reason that you couldn't use thorium in these reactors. The issue is more technological, really, in that the technology associated with using thorium is less mature, and that extends the timescales for licensing and getting reactors operational. So the philosophy is that these reactors work perfectly well without thorium. Thorium could be an evolutionary step if these reactors are a success.
So when I invited Dr. Taylor to give the talk, I told him that by the IOP policy, it should be a wide public talk. It shouldn't be technical. I see that from the question of the audience for almost the research conference. Yeah, so I'm really impressed by the kind of questions we get. So maybe I will ask a stupid question. You mentioned at the beginning that we are in such need of the energy, it's so expensive the energy. So why don't we use this nuclear technology? Why do we need gas at all? And we don't build so many of them. Who is preventing us from using that?
Yeah, great question. Not stupid. So I think the first issue is cost. Now, the best way for nuclear to replace fossil fuels as a source of generation would be if it's cheaper than fossil fuel generation. And at the moment, that is clearly not the case. So there are many benefits associated with using nuclear power, but you have to invest
money in order to see those benefits. So if you're a developing country that is prioritising getting electricity to the country, allowing quality of life to increase, then that's you're going with a cheaper option. That's it's bound to be driven by the economics. The other unavoidable fact is that the impact of accidents like Chernobyl had on the industry. It went from the nuclear industry went from a position where there was a huge amount of research and development going on into these sorts of designs to that almost being shut off. Almost instantly due to Chernobyl. So there is, there's more interest in developing these kind of designs now, and I think there's clearly increased safety, but those accidents set the industry back a long way.
I see. And Chernobyl, by the way, was worse than Fukushima?
It was. I suppose most people would say it's worse. It's generally regarded as the most severe accident that's ever happened here in terms of nuclear.
Okay, so last chance, if you want to ask a question to Dr. Taylor. Now is the time. Yes, please.
How much personnel would it take to maintain the kind of salt reactor? Because you say that the fuel is almost recycled in it. Would there be a lot of input required for it to work?
There's a big difference between the two designs here. In philosophy, the flex reactor, the UK design is, as I said, it's all about simplicity. So the idea then is that you require no kind of operator intervention. The reactor runs without operators in the control room, actively running that reactor, and the fueling of that reactor is less frequent than in a reactor now. So there's much less in the way of ongoing operation and then refueling for that reactor compared to a reactor operating now. The SSRW, I don't know if I ever explained the acronym, it's waste burner, the W. I should have said that, sorry. That is different. It's the philosophy there is to continuously refuel that reactor. So that will require much more in the way of ongoing operation to select the fuel that's going to be the channel that's going to be refueled, to perform that operation, to move fuel from the production facility to the reactor. Given that that fuel is very radioactive, there will have to be a lot of remote handling robotics in order to do that.
Okay, thank you. So if there are no further questions, before we thank our speaker, I'd like to remind you or inform you that we have the next IOP lecture, which will be on the topic of the Physics Olympiad, so competition, sport with physics. It will be given by Dr. Zhenya Shelichenko by the end of the month, so stay informed, more than welcome to attend. And there will be a little bit of time if you want to speak directly to the speaker. I see that there are a lot of experts there, so we will be there for a little while. You can come and speak to him. And that's it, so thank you again, Dr. Taylor.